Okay, this video covers chapter 3, number 6 through 10. So, what you really should do with each of these is try the problem and then take a look at the video and see if what you thought makes sense, that sort of thing. So, if you try number 6A, for example, and then press play and see if what you get matches, and then go back and try B. Or just try all of the assignment and then go look at the video. Um, Basically, you need to try each of the problems on your own, and this is here to help you get things that you don't understand figured out. Okay, so let's take a look at 6. For each of the following, compare the graph of g of x to the graph of f of x, the original graph with which is x cubed. Describe the transformation using words or a sketch. Okay, so if my g of x is a 3 in front of the x cubed, that tells me when it's out in front that it's stretched. So that's the only change that occurs is a stretch up and down, a vertical stretch this way. Okay, for b, now we have a 3 inside the parentheses raised to the power of 3. So this is like what we worked on Friday. Since the 3 is inside, that's going to be a compress horizontally, like this. And this one inside, 1/3, will be a stretch horizontally. So it'll appear wider. Now, since this is a cubic, I'll quickly do a little sketch of each. Let's say a regular cubic looks something like this. Well, the stretched one will be very skinny, and the compressed one will look kind of similar but at a different scale. And then the stretched one this way will look more like that, which also could be described as looking more compressed vertically. Okay, sometimes this will look like the function with a k in front of the x will look like a vertical stretch. Explain why when you look at the graph of g of x equals 3x to the third, it will appear to be stretched. Well, just kind of what I was talking about right there. If you compress, if you look at the stretch, doesn't it look narrower in addition? Okay, it looks compressed and stretched at the same time. And it's the same because the vertex is at 0, 0. If the vertex were in a different place, it would be sort of a different thing happening. So a vertical stretch looks skinny, looks the same as a horizontal compression. Okay. Next one. All right, given this original function f of x below, so here's our original. Generate the graphs in terms of f of x. Oh, let's see, find expressions that will generate the graphs. Okay, so we want the expression that would be what we get if we do this. Okay, so if this is our original here, what's different here? Is it squished down or stretched out? Now if I compare how high this one is with this one, that one's lower and this one's moved up. So I think that this is um, a vertical squash. So perhaps it would be something like 1/2 f of x. That's a possibility there. Now this one looks like it's just been made more narrow going this way. So perhaps that one is where I have a number greater than 1 in the parentheses. And this one looks exactly like the original except flipped over the y-axis. So that is what occurs when I have a negative in the parentheses with the x. Okay. Number 9, the meaning of decimal exponents. Well, what we know about decimals is that decimals can all be rewritten as fractions. So part A, express 0.7 as a fraction and rewrite this using a fraction. Okay, well 0.7 is equivalent to 7/10. If you use the formal way of naming decimals, you get the answer right in what you said. This is the tenths place, so we have 7/10, and the fraction is 7/10. So this is 10 to the power of 7/10. Okay, B, we can use the power law for exponents to break up this fraction into 2 factors. Find the value of C so that this works out. What would the value of C be to make this true? Well, 10 to the power of 0.7 is the same as 10 to the 7/10, and that can be broken up into 2 pieces of 10 to the 1/10 all raised to the 7th power, because 7 times 1/10, isn't that the same as 7/10? There we go. So rewrite your answer as a root raised to a certain power by copying and filling in the blanks of this. So this is doing the 10th root of 10 all raised to the power of 7. So why is it generally better to take the root first, especially when you're working without a calculator? Well, if you take the root first, it makes the problem smaller first, and then you make it larger. It makes the problem smaller. Do the calculation on your graphing calculator, or a scientific calculator will do. Any of the buttons that look like this, where there's an X root, you put in the 10 first, this symbol, and then the 10, and that will calculate that, and then you raise all of that result to the power of 7. Okay, so after doing that calculation, I see 5.01187, and it keeps going. The next one's 2, so I'm going to go ahead and round it right there. Now calculate 10 to the power of 0.7. How should this compare? What do you think? I think if we did it right, it should be the same. So let me check it on my calculator, 10 to the power of 0.7. And yes, I see exactly the same. They mean the same thing. Part G, Rashima notices that the answer is close to 5, and she knows that she could get closer by using more decimal places in the exponent. Use guess and check to find p to the nearest 0.001 so that p is as close to 5 as possible. Okay, so this is close to 5, and we want to get even closer to 5. So 10 to the 0.7 what gets us closer to 5? Well, the 5.01187, that's a little bit large, so we're going to need to lower this to 6. How about trying 0.68? Let's see, so 10 to the power of 0.68, I get what I get is 4.78. Okay, so this is too small. So let's change this now to 0.69 and see how close we get. So 10 to the power of 0.69. All right, that's a little bit closer, 4.8977. Okay, so we need to go larger than that. So the next one I'm going to try, I'm going to put something after the 9. How about 0.698? So 10 to the power of 0.698 and, ooh, even closer. Okay, I need you to continue working on that until you get that close. Okay, so this is something you need to finish. In a flash of brilliance, Rashima suddenly notices how to get several more decimal places instantly. What keys can you press on the calculator to do this? Well, I'm going to leave you to answer that. What key or what type of function do you think would do that? Okay, last question here. Okay, solve using powers of the same base. Okay, so 9x, I got a 3 here, a 3 here. What do you think the base is in common? Well, I think 3 because 3 squared is 9. So I'm going to rewrite this a little bit. So I'm going to rewrite the 9 to be a 3 squared. And that is raised to the power of x. And this equals 3 over 3 to the x power. Okay, well, let's simplify some of these. So 3 squared raised to the power of x, this is the same as 3 to the 2x power. And then I'd like this to be with the same base. What's the exponent on here? Well, it's a hidden 1. We don't have to write the exponent down if it's a 1. But I can use one of our rules to say that this is 3, since this is the same base, I can do 1 minus x. So 3 to the 1 minus x. Well, if these bases are exactly the same, and that would mean that these exponents must be equal to each other to make this statement true. So what x value would be there if I've got the exponents equal to each other? All right, like that. So I'm going to add x to both sides and I get 3x equals 1 and x is 1/3. All right, let's try that same thing with b. Okay, what is the common base? Well, 25 can be rewritten with a power of 5, a base of 5, and it's squared. So 5 squared times x gives us 5 to the power of 2x. And how can we rewrite this one? Well, this says 5 to the power of x, fifth rooted. Well, that's the same as times 1/5. So that can be written as 5 to the 2x equals 5 to the x times 1/5. It's x fifths. So if the bases are the same, I need the exponents to be equal to make it true. So 2x equals x over 5. Multiply by 5 on both sides and we get 10x equals x. And subtract 1x from both sides, and so I get 9x equals 0 and divide by 9 and x is 0. And that's that.